Huix Rutland, and he's going to talk about ultrafast intersystem crossings in aromatic ketones. Miquel,
thank you. Can you hear me?
Yes, very well.
Perfect. So thank you very much first, Chol and Mike and the rest of organizing committee for inviting me to give this talk. I am one of the crazy participants that decided to be on site. And this makes two difference with the virtual participants. The first one is that I have a very nice badge of the conference. And the second one is that I am enjoying a lot the exquisite hosting of South Koreans, which I also thank a lot. So without further delays, I start this talk, which I decided to do on this topic of ultrafast intersystem crossing that I started back in 2015. And I still have not understood everything, so I'm still continuing on this. So I will speak about Xanthone, which is an aromatic ketone with an exceptional intersystem crossing rate. I'll give you a lot of details on this, but just to frame a bit what is an ultra-fast intersystem crossing. If I can change the slide, yes. So intersystem crossings are fast essentially for three reasons. The first one is that we have what is called a heavy atom effect. So a metal or an atom that is from the bottom part of the periodic table. So here, for example, there is a rhenium complex, and within less than 100 femtoseconds, you see a build-up of triplets after exciting to a second singlet excited state. So that's one of the reasons of having a fast intersystem crossing. So due to the strong spin-orbit coupling. Another way is other complexes like this iron trisbipyridine, which have a weak spin-orbit coupling, has also a very fast intersystem crossing of the same rate as this one in the rhenium complex, less than 100 femtoseconds. And the reason is that when we excite to the singlet band, we are already in a place with multiple crossings with the triplet states, and that allows a very fast intersystem crossing, despite the spin-orbit coupling is about 4 to 6 times smaller. And finally, for organic molecules, of course, you don't have in general neither the heavy atom effect nor these bands of crossings. So the reason that is given for a fast intersystem crossing is that you have a strong vibrational overlap between singlet and triplet. And so that allows a fast rate, a fast transfer between singlet and triplet, despite having even weaker spin orbit coupling. So in the case of organic molecules, we are speaking about a range of 55 picoseconds. So it's not below the 100 femtosecond regime. But usually when you have a fast intersystem crossing in organic molecules, you have a pattern of an aromatic ketone. So an aromatic ketone is a carbonyl, which in an alpha carbon, it has a aromatic ring. So there are many types of such aromatic ketones, and they are having many uses. So here I just draw some basic backbones of some of the most popular ones. They are used as sun creams, as food additives, as colorants, antibiotics, in cosmetics, in perfumes, and so on. There is a lot of vitamins and other natural products that use such patterns also. And they have a very special photochemistry also. So these basic backbones, of course, then they have a lot of substituents, and they can be in different solutions. And all these changes, whatever you change in such aromatic ketones, you can change the rate of intersystem crossing in going from mid-fast to faster to extremely fast to a slower one to no intersystem crossing at all. And it's sometimes very difficult to rationalize why, for example, Xanthone, which I'm going to talk today, has a intersystem crossing of 1.5 picoseconds. And just by replacing this bridge by a carbon, you go to 40 picosecond intersystem crossing. So as I said, this is a job that I started a very long time ago, studying first acetophenone in 2016. At the same time, there was a surface hopping study by Maurizio Persico and Granucci, in which they computed using surface hopping a rate of 6 to 16 picoseconds. In here, we use wave packet dynamics. But today, I'm going to speak about this special one that, without having any heavy atom effect, has such a strongly fast spin orbit coupling. So in general, aromatic ketones have two types of states, which are pretty simple. So one which is called the n-pi star state. So you have a lone pair on oxygen that you transfer into a pi star state, mainly localized also on the carbonyl, but delocalized over the aromatic rings. And then you have another pi star transition, which is the lowest pi star. You have other pi star states which are a bit higher, which is a typical Huix transition described with such pi orbitals. So despite this very apparent simplicity of the electronic structure, if you use any of the electronic structure methods that are typically used for calculating excited states, you can get very different results, very different energies. So here I just show the spectrum of triplets, which I symbolize here. I put the spin multiplicity as a superscript, and then I put the nature of the state. So here I have the lowest two triplet states in the gas phase of Xanthone are the 3n pi star state and the 3 pi star state. So they are very different. For example, in TDDFT or in CASPT2, they are very different from the experimental one. So TDDFT is quite below and CASPT2 is quite above. So the good thing about TDDFT and CASPT2 is that at least they give the same order of states, and it's quite close, at least for as far as the energy gaps are concerned, for CASPT2 with respect to the experiments. With DFT, we use here B3LIB, but if we use a long-range corrected functional, we get also better energetics. In any case, this is one molecule that maybe Pierre-Francois can add in the Quest database, because it's quite tough to get the uniform result of the order of states for this molecule. In any case, the bright state is usually the singlet pi star state, which I just compute here. The vibronic spectrum. This is the only bright state that you have at this energy range of 300 to 330. And then you have this 1n pi star state, which is actually dark, and it can be below or it can be above, depending on the solvent that you use. So that is how you can actually change a lot the intersystem crossing rates and mechanisms for Xanthone. So for example, here I show 3 different mechanisms in vacuum, in ethanol, and in water that have been determined experimentally. So experimentally, actually, they can determine very well the order of the states from the singlet spectrum and the triplet spectrum. And then the crossings, they kind of devise them by using typical photochemical rules like L-Sayed rule that states that the 1 pi star state to the 3n pi star state is a fast intersystem crossing, and the 1n pi star state to the 3 pi star state is also a fast intersystem crossing. What it has been reported by experiments is that these molecules, Xanthone, can break Cash's rule, so you can have transfer from the S2 state to the triplets. And so the mechanism in vacuum, in vacuum you have the 1 pi state, which is the S2, and the n pi star state, which is S1. And then you have the pi star triplet as the T2. and the n pi star triplet as T1. And so the fastest transfers are crossing according to El-Sayed rule. But also you can have these non-adiabatic couplings that induce internal conversion between the singlets and between the triplets. In ethanol, you have a slightly different picture. You have the same spectrum for the singlets, but you have reversed states for the triplets. So the cross that we were having here for the fast intersystem crossing is now parallel. So you have a 1 pi pi star to 3 n pi star and 1 n pi star to 3 pi pi star. And for the case of water is a bit special because the 1 n pi star state is delocalized. Actually, xanthone is only partially soluble in water. And so this n pi star state is either above or below. It was not determined experimentally. So what is known experimentally is that you excite to the 1 pi pi star state, and then you somehow transfer to the 3 n pi star state, which is also delocalized over a range of energies. You can also have a back transfer to the singlet and have delayed emission, but most of the wave packet will go to the lowest triplet, which in this case is also 3 pi pi star state. So this is a bit the experimental picture for xanthone, and it was not known how from these 3 pictures you could extract this 1.5 picoseconds. So it was not exactly known what was the mechanism, because in here we can have first a non-adiabatic coupling acting, and so faster internal conversion and then intersystem crossing, or we could have also direct intersystem crossing from the S2 state. So there was a very complete study done in 2013 using rate equations. So this is a work basically done by Crystal Marion and co-workers. And they did an amazing job to study xanthone in the gas phase and in solution using the FTM-RCI for the energies, and then computing the rates by computing these spin orbit Byronic integrals, and then making a thermal average to extract these intersystem crossing rates. So the problem with this approach is that you can compute an intersystem crossing, but it was not able to compute the internal conversion rates. So you could not see the competition between the internal conversion with the intersystem crossing. And another problem is that this is a formula that works for a thermal equilibrium. And here we are in a photochemical problem, so we are essentially out of equilibrium. So despite the restriction, it computed some rates for xanthone in vacuum, in ethanol, and in water. And actually the rates were completely off what experimentally was obtained. So whatever, for example, in vacuum, they predicted that the 1 pi pi star to the 3 pi pi star state was taking 5 picoseconds, and that it was faster than transferring 1 pi pi star state directly to the 3 n pi star state. And this is a bit contradictory because it doesn't only break Cash's rule, but also breaks El-Sayed rule. And the problem here is that the energy gaps, I think, were too large with respect to the reality. So that's why this rate was computed so fast for such a forbidden transition. Anyway, what it was correctly predicted is that the 1 n pi star state to the 3 pi pi star state is the fastest intersystem crossing. For solvent calculations using this approach, what they did is to take a microsolvation. So they put 2 water molecules or 2 methanol molecules surrounded with PCM at the FTM-RCI level. And so they computed the rates with such a model. So for methanol, so it's not exactly ethanol, it was methanol, what they calculated. They gave 58 picoseconds, which is completely off from the 1.5 picoseconds for the S2 to T2 transition. And from the S1 to T1, it was 185 picoseconds. And for water, it was even worse because it was on the order of the nanosecond, so quite far from the 1.5 picoseconds that was experimentally observed. So that's how we jumped into this project. So we decided to make a model Hamiltonian, a diabatic model Hamiltonian, and perform wave packet propagation for xanthone in gas, in vacuum, and in solution. So this is the basic structure of the vibronic Hamiltonian that we're using. So we have a kinetic energy, the potential, which is in the diagonal of the Hamiltonian, and then we have the non-adiabatic couplings and the spin orbit coupling, which depends both on the vibrational coordinate in the off-diagonal part of the Hamiltonian. So the dimensionality of the problem is two singlet excited states, so the 1 n pi star and the 1 pi pi star, 4 triplet states, the corresponding triplets of n pi star and pi pi star, but also 2 higher ones that cross with the S2 state, and then the full vibrational dimension, which is 63 vibrations. So for the diagonal operators, the kinetic energy and the potential, we used Dushinsky rotations. So we calculated the minima at each of these states, and then we calculated the frequencies. We generated the Dushinsky rotations, and we added each of these potentials in a common basis of the ground state coordinate. So the ground state is our reference, and we project all the excited state frequencies on the ground state basis. For the non-adiabatic couplings, what we do is a fitting procedure. In this case, xanthone is a planar molecule, and there is only 5 modes which are really introducing non-adiabatic coupling. So in this case, we performed a potential energy surface cut, and then we feed at the TDDFT level, and then we feed these TDDFT potential energy surface cuts to our model by fitting these non-adiabatic couplings. And we obtain these non-adiabatic couplings between the singlet n pi star and the singlet pi pi star as being between 19 and 150 centimeters minus 1. So this is just one of the vibrations that of A2 asymmetry that gives one of the strongest non-adiabatic couplings, but there is not a lot of non-adiabatic couplings in here. It's just 5 modes that can induce this mixing between n pi and pi pi state by breaking the symmetry of the problem. For the spin orbit couplings, what we did is we added the absolute value of the complex matrix elements of the spin orbit between the states that we are considering. And we also added numerical differentiation to add this first order vibronic effects on the spin orbit coupling. The spin orbit coupling, just the part that does not depend on the coordinates, is the strongest one is between 1 n pi star state and 3 pi pi star state, which is 45 centimeters minus 1, much smaller than what we obtain for the non-adiabatic couplings. And the 1 pi pi star state with the 3 n pi star state is even smaller. It's just 5 centimeters minus 1. So then we took this model that we fitted, and we propagated using MCTDH. So this is the wave packet using MCTDH. So this is the ansatz for the wave function that we are using for the nuclei. So it has these time-dependent coefficients and these time-dependent products of functions. So we have an equation of motion when you plug this in the Schrödinger equation for the coefficients and for the basis functions that also depend on time. And then we are using the multi-layer version of it. So these wave functions actually come from a smaller MCTDH propagation. And here I show a bit the tree structure of our the construction of these basis functions from the upper layer to the lower layer. So we classify the electronic degree of freedom and the vibrational degrees of freedom in 4 different branches. And for the vibrational degrees of freedom, we classify them in low frequency, less than 200 centimeters minus 1. Then mid frequency between 200 and 2000, and then above 2000 we put them in the high frequency, and then we classify them by pairs using modes that belong to the same symmetry. This is the results that we obtain for Xanthone in vacuum. So we start our wave packet propagation from the S2 state, which is the bright state, the 1 pi star state, and we see a very rapid decrease of this population, and then a plateau that doesn't lose any longer in this 1.5 picosecond range. And this loss of population of the 1 pi star state is concomitant to the rise of the singlet 1 n pi star state. So, and then this singlet n pi star state is losing slowly population in favor of the triplets. So the black dashed line is the total sum of all the triplets. And here are the three components. So the first one that rises is the 3 pi star state. And then you have a small component also of the higher energy pi star state, which is this green line, and a very slowly building up of the triplet and pi star state. So if we feed these populations into a first order kinetic model, we can extract such a mechanism. So we start from the 1 pi star state, and we feed by exponential in here. We get actually two rates, 85 femtoseconds for 80% of the population, and 5 picoseconds for this extra 20% part of the population. Actually, we can see here that the non-adiabatic couplings play a major role at the beginning, and so the state that really transfers to the triplets is the 1 n pi star state, and not the 1 pi star state. So the basic photochemical rules are respected, and same for so the Kasha rule is respected in here, and the El Sayed rule is respected in here because the fastest intersystem crossing is from 1 n pi star state to the 3 pi star state, as one would have expected. So there is no fancy explanation about breaking the Kasha rule or the El Sayed rule in here. And what we have actually is very advantageous energetics, because here I plotted the potential energy surface connecting the conical interaction between the singlets and the minima of the singlets and the triplets with the ground state. So here the black arrow is where we excite. So this is the pi star state in blue, the singlet pi star state. So the gradient will bring the wave packet in its minimum, which is quite close to the conical intersection. And so that explains this 85 femtosecond fast transfer to the lowest singlet. And when we are here, I didn't show the scale, unfortunately, but this is a very small gap between the singlet minimum and the triplet pi star state. It's less than 0.1 EVs, and that explains that fast build up of population in the 3 pi star state, despite having only first row atoms and an organic molecule. So actually, you see here we have 2 picoseconds, but if I fit with an exponential the total triplet population, I get 1.5 picoseconds. So probably if I would increase this propagation of the wave packet beyond this regime of the 1.5, I could get a better estimate of these rates. But we are quite close to what it was expected in the vacuum. And just to conclude with this, we took this model by a lot of insisting of the reviewers of this article that is still under revision. They said, okay, I think you have a good model for the vacuum, but still you cannot reproduce the 1.5 picoseconds in water. And as you remember, I told at the beginning, in water, the 1 n pi star state, it is delocalized over a big range around the 1 pi star state. But if you take a model of microsolvation, and then you put that in a box of PCM, then you have a too strong hydrogen bonding in here that makes the destabilization of the n pi star state above the pi star state. So actually, where you excite, the pi star state is below the n pi star state, and so the the path of the wave packet is to go to that region in here, in which you have a crossing with the triplet n-pi star state. And this crossing is not leading to a very fast intersystem crossing, because the spin orbit in here is really, really small. And the vibrational wave function overlap doesn't help at all. On the other hand, so these results were more or less the same that were obtained with DFT MRCI. So they were seeing exactly the same order of the states as in here. But what we did is to make a little bit more, and we took this microsolvation model and we embedded it in a droplet of 300 water molecules that we treated at the level. And then we did QMMD dynamics. So in the short time dynamics, we see indeed that there is a lot of crossing between the n-pi and the pi star state. So the n-pi is the red one and the pi is the blue one. So we have the two states that are interchanging all the time. But if we make a longer time dynamics, we see that in fact, the n-pi star state is converging to a region which is below the pi star state. So in fact, we should consider two initial conditions, one in which the pi star state is S1, and the other one in which the pi star state is S2. And if we do that, we see that when the pi star state is S1, we have almost no transfer to the triplets within 1.2 picoseconds. Whereas when we have the normal order in which the one pi star state is S2, we have a rapid decay of the singlet state with a buildup of the S1, and then concomitant to the rise of the triplet in a rate that is similar to the gas phase. The non-adiabatic couplings are a bit less strong in this case, so with just 300 femtoseconds instead of 85. But the intersystem crossing rate is almost the same. So this is why in water we were not seeing, in water with microsalvation, we were not seeing a fast intersystem crossing, is because the order of the states was not the right one. So with that, I would like to thank the members of my group, especially Mark, who did most of this work when he was PhD, now he's postdoc in my group. I also have a starting position in 2022, starting from January, postdoc position. And then I thank all this financial support and you for your attention.
Okay, thank you very much, Miguel. Are there any questions? Yeah, Emmanuel. I see 3 hands. Okay. Maybe Emmanuel, you can start.
Yeah, thank you. Hi, Miquel. So you made it, you went there. Very good.
Yes. Difficult, but possible.
Congratulations. Thanks for the very nice talk. I did not really understand, maybe this is standard, but I'm not familiar with that, how you extracted the non-adiabatic couplings from your TD-DFT calculations. I didn't get that.
So I do a fitting procedure. So I define this error, which is the difference between the adiabatic energies and the adiabatic energies obtained by my model. And I minimize this error with respect to the non-adiabatic couplings. In that way, I get the estimate of the non-adiabatic couplings by 1D cuts.
Okay, and this is supposed to be like accurate, reasonable, or this is a standard thing, or?
It's a standard, it's easy. It works quite well by a lot of years using this procedure, and it always has shown quite accurate results for the dynamics. But I think it has never been really tested whether these couplings projected on the vibrational basis correspond to the real non-adiabatic coupling of an electronic structure.
Okay, I'm asking because I was trying, there are so many sources of errors that at the end, I mean, it's difficult to find out, I mean, right? So yes. There are so many, yeah, okay. Okay, thank you very much, very nice.
Okay, the next person with the hands raised on my screen is Professor Massimo Olivucci.
Yes, Miguel, congratulations, very nice, really.
Thank you.
Very neat mechanistic explanation. So one thing that I didn't get it, but probably it's very easy to explain. You were mentioning that there is a small gap between, in the gas phase simulation, that at the end of the day, there is a small gap between the n-pi star singlet and the pi star triplet.
Yes.
And that's, you pointed it to, you know, as, you know, a situation where, of course, the El-Sayed rule is obeyed. But I would think that there is a crossing also. I mean, maybe in another dimension, there must be some crossing, a real crossing between the triplet and the
there is a real crossing. Simply that.
So if nearby, you are in the region of the crossings, basically.
Yeah. So here is just because I used a geodesic path and I connected all the minima to explain a bit, to make a generalized reaction coordinate. But there is a real crossing, and it's quite close to the minimum of the singlet n-pi star state. So the wave packet arrived to the minimum, and then it fluctuates there, and all the time it finds this region of crossing.
Okay, thank you. That's my question. Thanks.
Okay, and Professor Michael Sherman, please.
Yep, just a quick question. For your explanation for the results of xanthone in water, would you predict then that the rate of triplet formation would be dependent on the excitation wavelength? Would that be an experimental observable? If you tune to the red edge or the blue edge of the absorption feature, you would expect to see a dramatic change in the triplet yield, right?
That's a difficult question, because actually experimentally they cannot really determine where is this n-pi star state, and I have not done the full dynamics. This is on my list of tasks of what is the real distribution of the n-pi star state. But yes, in principle, you could excite to different wavelengths and get directly in the n-pi star state and be blocked in the excited state. And this could explain actually why you have sometime delayed fluorescence at 700 picoseconds, because if you excite at n-pi star, you will get a very slow intersystem crossing, and then actually you get trapped in this region of the triplets, and then you can somehow get back to the singlets. But this is always difficult to simulate this, because you need to take the wave packet dynamics along with the MD dynamics. So you need to make a statistical average of all these simulations. So right now I have not done that, so I cannot give you a full answer on this.
Okay, let's thank Miquel one more time for the great talk. And then our last speaker for the session for today is Dr. Niri Govind from Pacific Northwest National Lab, and he's going to be talks about X-ray spectroscopy studies for transient metal complexes with TDDFT.
Thank you, Professor Young. Let me share my screen now. Please let me know if you see what is expected to be seen. Do you see?
Yes.
Give me 1 second. Is it good? Can you hear me clearly?
Yes,
Yep.
yes.
Okay. Thank you so much, Professor Choi, Professor Filatov, Professor Cho, and all the organizers for inviting me to give a talk at this conference. I appreciate this invitation. I would have loved to be there, but we haven't received approval to travel yet, so probably in the near future. So today I'll talk to you about X-ray spectroscopy studies in molecules and materials that we've done within the TDDFT framework using our developments in the NWChem code. And in keeping with the spirit of this conference with light matter interactions and theory with experiment, I'll show you 3 different examples where we've connected closely with experiments as well. So just to give you a sense of where I'm coming from, This is the state of Washington. And this is the Tri-Cities here where PNNL is located, which is in Southeast Washington. This is Seattle, just to give you a sense of where we are on the west side of the Cascades. So we are about 300 kilometers from southeast of Seattle. And the city of Portland is down here at the same distance, roughly about 300 kilometers. Here you see an aerial view of PNNL along the banks of the Columbia River. And this is our famous partner, famous neighbor, the LIGO Hanford site, which has been famous in the news for gravitational wave detection. So as I mentioned earlier, everything that I'd be talking to you about today is within the developments within the NWChem code, specifically within the linear response TDDFT modules. I will not talk about anything in the real-time module that we also have in the code. So just to give you an outline of the talk, as I mentioned earlier, I've picked 3 illustrations where we've used linear response TDDFT and different manifestations of it to touch base with 3 different kinds of experiments that we've made close contact with. In the first one, I will talk to you about the traditional XANEs, or specifically pre-edge XANEs. And I will illustrate that with a very, very well-studied system. We've studied, and many, many groups have studied, where the iron 2 hexacyanide in the 2+ and the 3+ oxidation states of iron. And using that as the baseline, I will talk to you about work that we did just about a couple of years ago, trying to elucidate the photoacquation process of aqueous ferrous hexacyanide, which is an interesting reaction. The second part of the talk, I'll talk to you about valence to core X-ray emission, which is, in a way, loosely speaking, is the reverse process from excitations. And I will show you examples of how we've been able to make contact with experiments with sufficient accuracy. And then finally, I will talk to you about 2-photon processes, as we've seen in a talk just from Professor Piesok's group, but how we've tackled it for the Huix process, in fact, and I'll show you some illustrations with that as well. So with respect to the first part, before I get really going into this context, for people who are uninitiated to X-ray absorption spectroscopies, typically, when you look at an X-ray spectrum, you normally have a very broad energy range that you see, and which could span about 500 electron volts on the x-axis in the energy scale, and it's typically divided into several regions. The pre-edge region is, in fact, the region where the rising edge is defined, where, in fact, these are transitions from the core orbitals to the highest, the lowest unoccupied orbitals, followed by higher transitions into the continuum, which is typically defined as the x-apse. And there's no real demarcation line where the transitions basically transfer over from the near edge over to the x-apse. In fact, so there are different methodologies that are used to treat the x-apse region, for example, that people working in X-rays are aware of. On the right side here, these are the different kinds of edges that you can encounter in X-ray spectroscopies. The K edges transitions from the 1s orbital. The L edges are essentially transitions from the 2p orbitals, and then so on and so forth. You can actually go up to the M edges, which is from the 3p, 3s, 3p, 3d orbitals, and so on. One thing that one has to keep in mind is, of course, in the community, is as you go up to shallower and shallower energies, you actually need more complex electronic structure theories to start tackling the X-ray spectroscopies of these lower edges, in fact, because the X-ray lines get more and more complicated with strong spin-orbit couplings, multiplet effects, and so on. So you might, the complexity of your theory also grows with the question you're asking actually at lower edges. For the purpose of this talk, we are just working on, basically, we just have examples that are focusing on the K edges and L edges respectively. So basically, for the X-ray absorption part of the talk, we essentially use an extension of TDDFT we solve the TDDFT response equations with a modification that only excitations out of certain selected orbitals are actually considered, and we don't have any restrictions on the final orbitals that can be excited into. And we make the modifications within the standard Davidson approach to make this possible, in fact. And we've done this quite a few years ago, in fact, and the details of this implementation is in this paper in 2012. So with that in place, I will basically introduce you to the very a very basic system that has been studied in X-ray spectroscopies, in fact, by many, many groups, which is basically this iron to hexacyanide system in the 2+ and 3+ oxidation states of iron. And there are very clear differences between the two spectrum. In fact, for example, for this lower one in the experiment, you see is the Fe3+, which is essentially transitions from the 1s to the unoccupied T2G and the 1s to the EG, because remember that these are actually low spin complexes. And in the Fe3+ state, you have an unoccupied T2G. And in the Fe2+ case, you basically have just unoccupied EGs. So very simply, through a broad brushstroke, you can actually see that the X-ray absorption spectrum essentially encodes this information. In the Fe3+, you get this initial transition to the T2G and then the EG. And in the Fe2+, you only get transitions into the EG. So in our simulations, in fact, where we've actually done very detailed simulations of this complex with a full QMM environment, we in fact can actually capture this energy difference between the two features. We can also see that we see the A and B features. And the energy difference between these A and B peaks, for example, are roughly captured with respect to experiment. And of course, since we're actually working within the context of TDDFT, you have to make sure that you have to use the proper exchange correlation and so on. And there is a whole validation process that has to be done before you actually get to do production calculations. And for those who are interested, I would point you to this paper where we've in fact looked at these two complexes over a broad range of spectra. So getting into this interesting question on the photoreactivity of aqueous Fe2CN6, based on what I just showed you for the very basic system. So this comes from, this was a very long-standing question. In fact, when you excite the system at less than 330 nanometers, there's a process called photooxidation that's actually most prevalent. Beyond 330 nanometers, in fact, you get this very specific process called the photoactuation, where what happens is the Fe2CN6 loses a ligand, a cyanoligand, and over a period of time, what happens is the cyanoligand wanders away and a water replaces it in that specific position. And for those who are interested from the experimental side, if you want to understand the experiments, the details of the experiments that were performed by my collaborators at the Advanced Photon Source, I recommend this Global XAS Journal Club talk that Professor Seidler organizes, which is very, very interesting because it's, and so this is a talk actually presented by Anne-Marie Mach last year, who led the experimental side of this work, in fact. So getting into some of the details, in fact, there was a very nice paper from the Chergui group in Switzerland, in fact, who kind of sketched out a mechanism as to what this photoacquation, how this photoacquation process basically goes through. And the interesting thing is what they found was they basically suggested, in the initial stage, when you basically strike this molecule with a photon, you in fact get into an excited state. In fact, and then the system, in fact, lands up in a triplet state. A portion of the system actually lands up in the triplet state. When once the system, in fact, sits in the triplet state, it in fact loses the cyanoligand. And over a period of time, the cyanoligand is basically replaced by water. And then basically the cyanoligand just wanders away in this case. And this process of, in fact, water replacing the cyanoligand is essentially what's called the photoacquation process. And they sketched out some timescales for this reaction to happen. In fact, in a rough sense, this early part of the reaction happens really very fast. And then this acquation process actually happens over a longer time scale. But what was missing in that paper, of course, was the details about how this mechanism actually happens. And this is where we collaborated with our collaborators at Argonne, because they had a new detection mechanism that was able to basically zone into one of these specific species. And so that was where they contacted us to collaborate with them. So we assumed, we basically, instead of looking at the system completely as a whole, we started looking at we did the QMM MD simulations in segments, if you want to call it that way. So we assumed we didn't worry about the very early timescales because we didn't really have very specific experimental data. So we assumed that the system just is on the triplet state, and we propagated the system on the triplet state. And then what ends up happening is over a period of up to about 1 picosecond, you actually see a cyanoligand actually coming off, which we call T1. In fact, we're still trying to clamp down that early time scale, in fact, because the experimentalists don't really have the resolution to tie that down yet. But in our simulations, we did see the cyanoligand wander off the system, in fact. But what happened after that was the most interesting thing. Once the system, in fact, arrived at this pentacoordinated system, what we noticed in our simulation was there was actually an oscillation between a square pyramidal and the trigonal bipyramidal. And so, which is, in fact, if you look at it chemically intuitively, in fact, you would guess that, in fact, because saying, okay, there are two 5-fold coordinate system species, so why not have the system oscillate between the two? And we, in fact, saw this oscillation in our simulations, which gave you a time scale of about 3 picoseconds, in fact. So experimentally, what is observed is, in fact, is a superposition of the X-ray absorption spectrum is, in fact, is a superposition of these two species, in fact. And so we were able to simulate, this is the top panel here is the X-ray absorption thing, X-ray absorption KH at the ion KH, and these two bottom two are the bottom two calculations. And you see, for most part, in addition to having a pretty good agreement, but we don't see too much difference between the calculated KH, ion KH versus the experiment. And we also simulated the species in the aquated regime, in fact, where the water replaces the cyanoligand, and we were able to basically produce the experimental spectrum again. So of course, from our theoretical calculations, we were able to see at a broad brushstroke what was happening, in fact, at these various zones over the whole course of this whole mechanism. But what it did not answer is, of course, is the specifics of the species and the residence times of how long the system lives in one versus the other, and so on, as well as the long time scale that is actually observed in the experiment of 20 picoseconds for the actuation. So taking a step back, the question now is, how does this FE-KH Zanes compared to the model complex that I showed you earlier? And as you can see, this is the model complex, which is only transitions to the EG like I showed you earlier. You see that in the pentacoordinated species, you in fact get this feature that is actually redshifted away from the KH for the model complex. And likewise, you see the same thing happening. There's a redshifting, as well as, there are these relative shifts that we observe from the calculations that are actually borne out in the experiment as well. And the reason why you see a larger feature actually in the pre-edge in these cases is because these features tend to pick up a dipole, in fact, a dipole contribution, as opposed to the model complex, which is purely quadrupole for most part. So in fact, we in fact get the right kinds of features that we see in the experiment. In fact, so the theory is actually reasonably accurate in sense of getting the correct trends. So this kind of just basically reinforces what I just told you earlier in the previous slide, that we were able to get the broad brushstrokes of the overall mechanism, but that didn't answer the long time scales of why, after a quick loss of a cyanoligand, which happens in about 1 picosecond, why does the actuation take 20 picoseconds to actually occur? So for that, what we did was we did something different. So what we went back and looked at the pentacoordinated system, and we wanted to understand what the residence times are, in fact, of these two pentacoordinated isomers. And chemically intuitively, you can see that, you can have a square pyramidal and the trigonal bipyramidal. It's only the square pyramidal that gives you an opportunity for a water to attack the system, whereas the trigonal bipyramid doesn't give you that opportunity. And when we did these residence times using the Steinhardt order parameter by tracking the 5-fold coordination of the system, we noticed that the system actually resides in this conformation only for 500 femtoseconds of the total 3 picosecond oscillation. So this beautiful dynamics, in fact, tells you that the system doesn't live in these two isomers at the same rate, for the same amount of time. So this gives you a very nice, beautiful explanation for why the 20 picosecond happens over the long time scale, because you only have about 15% probability for this to happen. So we brought all of this together, in fact, in this nice paper in 2019, which was in close collaboration with our X-ray spectroscopists collaborators at APS. So there are a few things that we're still working on. In fact, these early time scales that I was talking to you about, how the cyanoligand comes off really at the very early time scales and how the end system even ends up on the triplet state. So those are regions of the spectrum that we're actually still working on because the experimenters don't have the resolution yet, but we're actually doing the simulation so that we'll be ready when they're actually ready to actually measure these signals. So for part 2 of the talk, I'll talk to you about how we've used TDDFT to look at a specific process called valence to core X-ray emission. And I'll show you how it complements X-ray absorption Xanes, for example, that I showed in the first part of the talk. And here I'll focus on some examples that we've done with transition metal complexes, as well as solid state compounds. And then I'll go back to this photo actuation system and show you a predicted signal that we've proposed to our experimentalist friends to see if they can actually measure it. So what is valence to core X-ray emission? And for people who are uninitiated, when you create a 1s core hole in a system, in fact, you get the system relaxes in many different ways. The most strongest signals that you get are these things called the K alpha lines, which are of course spin orbit split between K alpha 1 and K alpha 2. And then you get a weaker K beta line, in fact, which is roughly about 8 to 10 times weaker than the K alpha lines, and so on and so forth as you go up to the valence levels, where you end up seeing these satellite peaks, in fact. So what I call the valence to core region is, of course, are the de-excitation transitions that happen from the highest occupied molecular orbitals down to the 1s. So if you stop and take a step back, you can right away see that the Xanes, which gives you transitions from the core orbitals to the highest, to the lowest unoccupied orbitals, when coupled with the valence to core X-ray emission, kind of will actually give you the full bonding picture of the ligand, in fact, of the complex that you're interested in, because you get information about the highest occupied molecular orbitals from this spectroscopies and the lowest unoccupied orbital from the Xane spectroscopies that helps you give you a nice full picture. So the interesting thing that's been happening in light sources as well as instrumentation, of course, now is this very weak region now is actually resolvable quite well. And this is the rich chemistry, in fact, that's encapsulated. So this is the focus on what we're actually interested in this portion of the talk. So in a rough sense, what you do is you core excite a system to a continuum, and you basically look at the de-excitation transitions from the highest occupied molecular orbital. So in NWChem, what we've done is we've developed this within the context of the response equations that I'm showing you earlier. So what we do is you essentially perform a neutral ground state calculation first, then you prepare a relaxed core ionized state as a new reference, because you need this new reference into which you want to de-excite into. And then you basically solve the response equations now, looking at these negative transitions down into the 1s core hole, or 2p for that matter. And so the nice thing that you get with this now, using this response framework, is you get the natural multi-determinable character of the excited state that you get naturally with the absorption. So think of this as a reverse, a process it's the reverse of what I was showing you in the first part of the slide. And we've explained this for now, formalism, and illustrated this with transition metal complexes about a few years now. In fact, it's been out there for about 5-6 years already. So how does this actually work? So this is the first set of complexes we looked at. So we looked at a whole range of 3D to 1s transitions for a whole bunch of 3D transition metal complexes, ranging from over a whole range of spin states, in fact. And of course, with the caveat that, like I was mentioning earlier, that you have to choose your exchange correlations carefully with all of those things that have to go, and which I don't explicitly mention here. But once you've done that homework, you can see that the protocol, in fact, works quite well. In fact, you can start assigning these, the blue peaks on top are the experiment, and the curves below are actually the theory. So you can actually start basically assigning these features that you see in the experiment quite well. So recently we had access to 4D complexes as well, because our collaborators at SLAC had a new setup that they were in fact able to probe the 4D to 2P transitions valence to core X-ray emission data. And so they gave us access to this data, in fact, for a whole range of model ruthenium complexes, in fact, in the 2+ and 3+ oxidation state. And what is interesting, in fact, is the jagged line on top is the experiment, and the theory is right at the bottom. And as we saw in the 3D transition metal complexes, we were really pleased to see that we can actually see this thing even in the case of the 4D, in fact. So what's the take-home message of this, right? Because for most of these valence to core transitions, you get a very strong main peak, and you get some kind of a tail that's simply handled. So what this means is, in fact, that the contribution of the transition metal, the 4D or the 3D, the main peaks, in fact, the intensity of the peaks, in fact, gives you the transition metal contribution to the spectrum. And what that peak encodes is the oxidation state as well as the ligand field strength. So this is a very nice spectroscopy that pairs really well with the Zanes that I showed you earlier on. And for details, you can actually see this paper that was published earlier this year in Chemical Science, and where we give all the details of the calculations and so on. So we've also looked at solid state complexes. Okay, so not molecular as well. But when I mean solid state, these are cluster models because the implementation is within the cluster approximation in the TDDFT module and NWChem. So we wanted to understand what if this approach actually works quite well for solid state systems. And here we were looking at certain battery materials that were brought to us from Professor Seidler's group at the University of Washington at Seattle, where he in fact has a lab-based setup that can actually measure these spectra. In fact, you don't have to go to a beamline; you can measure it in his lab. So as you can see here, we looked at a range of complexes where we looked at different oxidation states of vanadium. And you can see that, we are in qualitatively good agreement. In fact, the line shapes are mostly captured. So of course, there are some peak height differences, which we potentially can attribute to the fact that our models are not perfect. We don't work in the periodic environment. We have a cluster model, so we work within a cluster approximation. But within that framework, we can see that we can qualitatively actually pick up the features that we see in the experiment quite well. And so this is a very, very nice development that we thought we could basically rely on actually looking at new systems. So going back to this photo actuation problem that I showed you earlier, the first thing that we wanted to understand was, can we basically use valence to core X-ray emission for transient species? In fact, so we had these two transient species that were oscillating over a time span of 3 picoseconds. So we wanted to say, okay, let's calculate the valence to core X-ray emission for these two species. And of course, you can see there, just like we saw in the Zane spectrum, there's not much to pick apart between these two spectra. But what is interesting, you do actually see small little chemical shifts here at the higher end, in fact, here. And as I mentioned to you, since the system lives in this preferred conformation only 15% of the time, remember when you construct an X-ray spectrum, you would have to suitably weight the spectrum as well. So we don't believe we can actually see this, but this is a theoretical calculation. But we've proposed this to the experiment, of course, to see if they can actually increase their resolution, for example, tease these two species apart at that scale. So this is a work in progress that we've proposed to our experimental friends. So the final part of the talk is, in a broad way of looking at it, is actually combining absorption and emission and bringing the two pictures together, in fact. And I'll show you how we've done this within a simplified linear response TDDFT approach. And I'll illustrate this with the 2D, 4D RICs for ruthenium-2, ruthenium-3 complexes that I just showed you, in fact, for the valence to core X-ray emission. Now, as we saw in Professor Piesok's talk, the two photon cross sections are, in fact, given to you by this expression here, which is the Kramers-Heisenberg expression. So you see two key quantities. You actually see a matrix elements going from the ground state to some resonance state, and then you basically get a final a second matrix element, basically, which is which takes you to some final state. In fact, so there are essentially two matrix elements that have to be calculated. And in a sense, you have to basically calculate that transition moments between excited states. So for people, practitioners of TDDFT, you know that the transition moments between excited states are actually not available in any code. So you basically have to write this code to basically calculate the transition moments between excited states, because you always get the transition moments with respect to a reference state. But from a formal perspective, in fact, you do have access to those quantities by going to quadratic response, because these are the double residues of quadratic response theory. But it's also known that, with approximate theories like TD-DFT, for example, or even other manifestations of approximate theories, that the quadratic response does have a spurious pole structure, which where basically Dalgaard has shown all the way back in 1982 that the transition energy between two excited states, when it matches the excitation of any other state, you in fact get a pole in the denominator that can't be canceled out. So you live within that framework, and it's kind of a landmine that you have to be very, very careful about, especially when you use quadratic response theory. The interesting thing, of course, is quadratic response theory is also a lot more expensive than linear response TD-DFT. So if we want to study large complexes, you have to pay a huge computational price. So going into this problem, we were aware of these potential limitations that one has to be careful about. So we asked a very simple question saying, okay, can this be worked out within linear response TD-DFT? And of course, we said, the CI vectors that you calculate with the linear response TD-DFT solution are actually quote unquote good wave functions, if you want to call it that way. And we call it the pseudo wave function approach. And when you can actually rewrite these matrix elements in terms of the solutions of the Caseda equation, in fact. And what you've done essentially, what I like to call this approach a static approach, because you're missing the second order polarization because of the quadratic response. But we know what we've missed. So the question now is, does this give us a reasonable way of actually looking at the spectrum that we've been given access to? So the details of this formalism and this implementation are actually in a JCTC paper that came out in 2021. So before I get to the Huix results, I want to show you, because if you look at the first part of this thing, the first matrix element is essentially a core excited state. So we want to know how well our linear response TD-DFT does for the core excited state. So we went back to these same complexes that I showed you in the valence to core X-ray emission. And this is the data on the left side, and these are the calculations. And the data actually has two different kinds of data. That is a standard Zanes and a Herfte Zanes for people who are working in X-ray spectroscopies are fully aware of. But you can see that the theory matches the experiment very well in this particular case. And for details of this specific calculation settings and so on, I refer you to this paper again that I mentioned earlier on. And so this gave us confidence that, in fact, that the first part of the spectrum, in fact, the first set of matrix elements would actually be correct as far as we are concerned with this. So we went ahead and implemented the pseudo wave function approach. And these are the Huix maps that you get for these for three complexes, for example. And these are the Huix maps which have the energy transfer axis and the absorption axis. And these lines are essentially the resonant lines at which the Huix cuts are actually created. So you create these cuts, and these are the plots that you get at these specific cuts, in fact. So notice right away that you see that the experiment and the theory for the various Huix cuts are actually in pretty good agreement. There are some detailed differences at the higher end side, but I would say, these calculations are actually qualitatively in agreement. That allows us to give us an understanding and assignment. We can actually help the experimentalists assign these features. The one obvious difference, of course, between the theory and the experiment that you see is the elastic line, which is essentially what goes in, what comes out. And the elastic features are actually largely overestimated in theories. And if you see Huix calculations done with other levels of theory, you actually see the same feature, in fact. And this could be discrepancies, right, that are there both in the experiment and the theory that we don't have a full control over. But the elastic line is not the most important, interesting thing here. It's the energy transfer that we're actually interested in this particular case. So it's the energies that are off from the point zero onwards. So in a nutshell, in fact, this is actually really good. So at the end of the day, we have this approach that helps us get around a full quadratic response approach, and basically kind of sneakily get access to these signals through a linear response sense. Now, just think of it, right? So in this particular case, we had to basically couple two sets of excitations. Think of the excitation, the initial excitation, which is a core excitation. The final state actually leaves the system in some kind of a valence state. So you literally are actually coupling core states and valence states in this 2-photon process. And in some of these calculations, we actually had to calculate an order 1,000 valence states, valence excitations, and of the order of 100 core states, in fact. So this is a fairly expensive calculation if you had to go through quadratic response theory. So this approach gives you at sort of, at the cost of roughly 2 TDDFT calculations, you can in fact start making very, very quantifiable predictions of the experimental measurements. So what I've given you a sense is, how you can extend TDDFT sort of in a black box sense to tackle XANEs as well as valence to core X-ray emission and now Huix as well, in fact. So what we're actually doing is we're including the spin orbit effect so that we can actually start looking at more complicated transition metal systems. And this is an ongoing project. And hopefully I'll be able to share that with you soon. And then I've also shown you a Huix approach, for example, right, using sort of the cost of 2 TDDFT calculations to provide you the necessary signatures that we can basically capture most of the observed features that we see in experiment. And we're also including the spin orbit effects as well as we speak, in fact. So before I end, I'd like to acknowledge my collaborators. And it's actually very valuable to have really good experimental collaborators, in fact, as you're developing theory, because to have access to really high quality data, in my case, it's all X-ray absorption and X-ray spectroscopies. So I'm really thankful to my collaborators at the University of Washington, Seattle, Professor Munira Khalil and her group, Linda Young and her group at Argonne, Bob Schoenlein and his group at SLAC, and Professor Jerry Seidler and his group in UW Seattle Physics. And last but not least, I'd like to thank my collaborators, my former postdoc, Daniel Nascimento, who is now an assistant professor at the University of Memphis, Amity Anderson, who is a staff scientist at PNL, and Professor Shal Mukomal and his group for long collaborations over the last several years. With that, I'll stop and take questions.
Okay, thank you, Dr. Govind, for the wonderful talk. Any questions or comments from the audience?
Okay, so let me have questions. First of all, thank you very much for joining this conference. I really appreciate it. Also, I really enjoyed your talk. So extending the TDDFT to the very difficult case of X-ray and core electrons. So we are also kind of developing different variations of TDDFT. So we are thinking that we also trying to do similar things, as well as also you actually developed a real-time TDDFT too, right? So
yes.
That's also, we love to follow your track. So maybe in the future, we would like to have some collaborations. So I'm wondering how good if you remove the core electron from this, and so you got a new relaxed state, right? And then you do the response on top of it. How? So I don't have any guess. So could you tell us the accuracy and how easy that is? Because it's kind of difficult for me to really optimize that.
Right. So basically, if I understand your question, so if you create a core hole state, you want to be able to stabilize that and get you a variational solution for that. Mm-hmm. So in NWChem, we've implemented what's known as the maximum overlap method.
Oh,
so basically, you start with a core hole state and you keep track of the overlap, and then you basically have these non-off-bound type populations after that. So with that, you can get a maximum overlaps and a variational solution that you can basically use as your reference. Now, you have to be careful, of course, right? You know, it's not always possible to converge every state that you prepare. But the one thing you can rest assured is when you do core excitations, you're mostly single determinant dominated in the specific case. So you're basically strongly single determinant dominated. So you actually can get a variation solution in this particular case. So that's what we've actually used for all these, especially for the valence to core X-ray emission to get this new reference state.
Okay, thank you very much.
Okay, Emmanuel, do you have a question?
Yes, thank you very much. Actually, my question is connected to the previous question, a very naive one. But so I was wondering, before you actually do TDDFT, do you get something like reasonable with the bare CONCHAM orbital energies in terms of excitation energies, or the TDDFT is really doing a lot?
Well, I mean, are you just talking about the CONCHAM differences, eigenvalue differences, for example?
Yes, for example, yes.
Yeah, so this is what I was saying, right? What's not mentioned in a short talk like this is you have to go through that process, you know, to look at the exchange correlation and so on. You have to do your homework. And then what we want to do is when we want to select a set of systems, we don't want to change up the exchange correlation for every system we want to do. So we pick an exchange correlation, and that's the homework part. You have to basically make sure that you're in the right space first before you start doing TDDFT on it. And so there's a bit of work there. And of course, you want to be able to use the same exchange correlation, so that kind of gets you sort of it's a compromise, right? So you would do well in some cases, not so well in the other cases.